Hello friends, welcome to H2 Academy. In the last lecture, we have discussed up to question number 3. So we will discuss question number 4 onwards in this particular lecture. So let's start our discussion. So what is given in the question? Assuming that in a cannon, the force on a ball depends only on the volume of the gas generated by the gunpowder. Show that the ratio of final velocity of the ball when the gun is free to recoil to its velocity when the gun is fixed is under root of capital M upon small m plus capital M, where M and M are the masses of gun and the ball respectively. So we have the two cases here. Okay, so case 1 and case 2. In the case 1, the gun is free to recoil, and in case 2, gun is fixed. In case 2, gun is fixed. There is no recoil velocity. Here, gun is free to recoil. Okay, and we have a ball of mass small m. Ball of a small m. Okay, so let us consider small v as the actual velocity of the ball in the case 1 where gun is free to recoil, and small u be the velocity with which the gun recoils. In the case 2, there is no recoil velocity. Let us consider capital V as the actual velocity of the ball. So since it is given in the question, the force on the ball depends only on the volume of the gas generated by the gunpowder. Okay, so there will be the conservation of energy. So the energy in case 1 will be equal to energy in case 2. Also, in case 1, there is no external forces applied in the horizontal direction, so we can apply the principle of conservation of linear momentum. So let's start. So in the case 1, the total energy generated is half of a small m into small v square plus half of capital M into u square, and applying the principle of conservation of linear momentum. So the momentum before firing will be equal to momentum after firing. So momentum before firing is 0 is equal to m into v minus m capital M into small u. Capital M into small u. Okay, so from here we have u is equal to mv upon capital M. Okay, and in case 2 we have this one. Here the gun is fixed, so the energy will be half of m into capital V square. And this is equal to, so we can equate both these expressions. So we have half of m capital V, sorry, small v square plus half capital M u square is equal to half m into v square. So from here we have half gets cancelled, and let us put the value of small u. We can put here. So m into v square plus half we have cancelled, so we have capital M into u square. This is m square v square upon m square is equal to m into capital V square. So let us cancel the m portion, so m gets cancelled. So we have, and capital M gets cancelled. So we have a small v square. So we have a small v square into 1 plus m upon capital M is equal to capital V square. So from here we have small v square upon capital V square is equal to capital M upon capital M plus small m. Okay. So from here we have small v upon capital V is equal to under root of capital M upon m plus small m. So this is what we have to prove. Okay. So let us discuss question number 5. A gun of mass capital M fires a shell of mass m horizontally. Okay, so there is a gun of mass capital M which fires a shell of mass small m horizontally. Okay, and the energy of explosion is such that it would be sufficient to project the shot vertically to a height h. Okay, so this energy, the energy that is generated is sufficient that it would. Let us take the gun in this orientation. Okay, so there is a shell. So this energy that is generated here is sufficient that it would project the shell to a height of small h. So this is a height h. So let us consider the initial velocity as a small u. Okay, and this energy is able to project the shell to a height of small h. So the potential energy will be mgh. Okay, if mass of the we have taken the mass of the shell as a small m. Okay, so the potential energy generated will be mgh, and the initial kinetic energy will be half mu square. Okay, and the final kinetic energy will be 0 because here the final velocity is 0. Okay, so the change in kinetic energy is stored in the form of potential energy. So the change in kinetic energy is stored in the form of potential energy, change in potential. So here at initial position potential energy is equal to 0. So we have half mu square is equal to mgh, and this is equal to capital E, that is energy generated at the time of firing. So the energy generated will be, so let us consider a small v with the velocity, actual velocity of the shell, and capital V with the velocity with which the gun recoils. Okay, so let us write down these statements. So let a small v be the actual velocity of shell, and capital V be the velocity with which gun recoils. Okay, so the energy generated will be half mv square plus half capital mv square. This is equal to mgh. Also, since there is no external forces that is acting in the horizontal direction, so we can apply the principle of conservation of linear momentum. So applying principle of conservation of linear momentum. Okay, so this is equal to m small v is equal to capital M into capital V. So from here we have to find the capital V, that is velocity of recoil of the gun. So let us find small v. The small v is equal to m capital V upon small m. Let us place this value here. So we have let us further simplify this. So we have the energy generated is equal to half small m into small v square plus half capital M into v square. Okay, this is equal to mgh from here because energy is conserved. So we have half m into v square is m square capital V square upon small m square plus half m v square is equal to mgh. Let us further simplify this. So this gets cancelled. So we have m half we have half mv square into 1 plus capital M by small m is equal to small mgh. Okay, so we have half m v square small m plus capital M upon small m mgh. So from here v square is equal to 2m square gh upon capital M into capital M plus small m. So from here we have capital V is equal to root under 2m square gh upon m into capital M plus small m. This is the velocity of recoil of gun. Okay, so let us discuss question number 6. How we can solve this. A shell of mass small m is projected from a gun of mass capital M with a explosion which generates the kinetic energy E. Prove that the initial velocity of the shell is 2em upon m plus capital M. It is assumed that the instant of explosion the gun is free to recoil. Okay, so there is a gun like this of mass capital M, and there is a shell of mass small m. Okay, so let us consider. So let small v be the actual velocity of shell, and capital V be the velocity with which gun recoils. Okay, capital V, and this is small v. So the energy generated will be half m v square plus half of capital M into v square, and since there is no external forces acting in the horizontal direction, so the momentum before firing will be equal to momentum after firing. So the momentum before firing is 0 and momentum after firing is m into small v minus capital M into v. So we have to find the initial velocity of the shell. So we have to find initial velocity of the shell, that is, so let us find capital V here, m small v upon capital M. This we can place in this expression. So we have E is equal to half mv square plus half capital M into m square small v square upon m square. This gets cancelled. So we have V is equal to half mv square, from here 1 plus small m upon capital M. Okay. So this is equal to half m v square capital M plus small m upon capital M. Let us find this. So we have to find the small v. So we have 2e upon m is equal to capital M plus small m upon capital M v square. So we have v square is equal to 2em upon m into m plus capital M. So we have v is equal to root under of 2em upon m plus capital M. Okay, this is the initial velocity of shell. Okay, so we will discuss further questions in next particular lecture. Thank you.